This is crash course. We will discuss the crash course in two parts. One in the form of synopsis discussion, where concepts will be repeated, revised, and important equations, important applications are discussed. Two numerical problems pertaining to these concepts are also discussed in the second part. The first chapter for our discussion is laws of motion. You know that this particular chapter is all about the discussion of force, correct? Let's try to understand what that force is and how to apply this. You know that force is an agency which is responsible for change in the state of motion. Change in the state of motion. When we say change in the state of motion, it may refer to an object moving or probably that of rest also. Remember, this force, which is represented by the symbol F, is a vector quantity and its SI unit is Newton and it is represented by uppercase N. This is the representation. Now, an object may be under the influence of one force or several forces. If the object under consideration is under the influence of several forces, for example, here this is one force and this is the second force, this is the third force, etc. We can call them as F1, F2 and F3, etc. Then we can think of a single force which replaces all these forces, and that is net force. And you know that the principle of superposition tells us that net force is given by vector F1 plus vector F2 plus vector F3, etc. Now, if there are two forces F1 and F2 acting at a point on an object, subtending an angle theta between them, then we know how to find out the resultant force. That's right. Law of parallelogram of vectors gives us this, and the resultant force is equal to square root of F1 square plus F2 square plus 2F1 F2. Cos theta is the resultant or magnitude of the resultant. Now, if the resultant of these two vectors is F, and if it subtends an angle alpha with the first force, then we also know that tan alpha is given by F2 sin theta divided by F1 plus F2 cos theta. That's right. The resultant is given by this set of equations, magnitude and direction. Suppose I consider an object which is under the influence of several forces and it is in equilibrium. Let's assume that the object is in equilibrium. Now, what is the meaning of equilibrium? You can all recall, equilibrium implies net force is equal to 0. The vector sum of all the forces is equal to 0. Suppose we consider an object under the influence of three forces, for example, F1, F2 and F3C, and the object is under equilibrium. That means the net force is 0. Then we can write F1 vector plus F2 vector plus F3 vector is equal to 0, or F3, which is equilibrant, is minus of F1 plus F2. Now, if the forces are coplanar, if these three forces are coplanar, then we know that F1 vector, or say magnitude of the vector F1 plus F2, must be greater than or equal to F3. And of course, this is greater than or equal to F1 minus F2. That's right. So we can write F1 plus F2 greater than or equal to F3 greater than or equal to F1 minus F2. Now, when we say equilibrium, remember, it generally refers to two cases. One is static equilibrium and the second is dynamic equilibrium. What is the meaning of static equilibrium? Static equilibrium means it is at rest, the object is at rest. Net force is 0. And not only net force is 0, the object is not moving. The object is in dynamic equilibrium means then the object is in motion but with constant velocity. So again net force is 0, you may notice. Velocity is constant implies acceleration is 0. Acceleration is 0 implies the force is 0. That is right. Now this static equilibrium can be of three types. We can say stable, unstable, and neutral. Stable, unstable, and neutral. These are the three types of static equilibrium. Remember, this important concept is to be kept in mind. Suppose we consider this idea of equilibrium. The net force is given by 0, and if it is under the influence of several forces, for example here, then the force is equal to minus du divided by dr in the case of conservative force. Remember this important concept. In the case of conservative force, force is related to potential energy in this form. Let us go back to this concept one more time. Suppose we have three forces F1 and F2 and F3. This is what I said at the beginning. Now, this system is in equilibrium, or the object under consideration is in equilibrium. Then the condition for equilibrium can also be written using something known as Lamy's theorem. What is that? If this angle is alpha, if this angle is beta, and if this angle is gamma, then according to Lamy's theorem, you can write F1 divided by sine alpha is equal to F2 divided by sine beta is equal to F3 divided by sine gamma. This is the condition for equilibrium as depicted by Lamy's theorem. So, in order to understand equilibrium, remember, the object needs to be under the influence of 0 net force, 0 acceleration, maybe static equilibrium or dynamic equilibrium, right? And we have seen that the resultant can be obtained under the on an object which is under the influence of several forces using parallelogram of forces, or if it is in equilibrium, then even Lamy's theorem tells us the relation between these forces. Having said that, in order to introduce one of the very fundamental ideas in laws of motion, let us look at the forces available in nature, basic forces available in nature. We can say basic forces available in nature. What are the basic forces available in nature? You all know this. For PU examination, you have studied these things. There are 4 types of basic forces, or we can say all the forces can be classified into one of these. You can say in the order of increasing magnitude, we have gravitational forces, electromagnetic forces, and weak interactions or weak forces, and strong nuclear forces. So these are the 4 types of forces available in nature. Remember, gravitational force is between masses, electromagnetic force is because of charges, weak interactions occur during nuclear reactions, and nuclear forces exist between nucleons which generally are very close to each other. So these are different types of forces available in nature, classified into 4 different categories. This is a very quick introduction to forces. However, when we come to the applications, the first thing that we learn is Newton's laws. Newton's laws of motion, generally known as NLM or laws of motion. Newton's laws tell us how the force plays a very important role during the motion. Let's try to understand this one. You are all familiar with this. Let's just have a quick recap of this thing. According to first law, you may wish to recall this, every object continues in its state of rest or of uniform motion in a straight line unless it is acted upon by a force to change that state. So, if we go back to the earlier statement, it tells us force is an agency which changes the state of motion. That's right. So, simple qualitative law which tells us that in order to change the state of motion, we need force. This is also known as law of inertia. And you know that mass is a measure of inertia of an object, right? And this actually introduces us 2 important things. One is inertial frame and non-inertial frame. If the first law is valid in a particular frame of reference, then this is known as inertial frame. So, a frame of reference in which first law is valid is called inertial frame. And if a frame of reference is at rest or in uniform motion, then it is called non-inertial frame. It is called non-inertial frame. Second law of motion, Newton's second law. The first law is a qualitative law which tells us that force is required to change the state of motion. The second law tells us, or it gives us, the magnitude of the force. According to second law, the rate of change of momentum of an object is proportional to the resultant force acting on the object. So, it actually introduces the concept of momentum. You know that momentum is a vector represented by the symbol P, which is nothing but product of mass and velocity. So, now second law tells us that the force is directly proportional to the product of mv, or rather rate of change of mv. That's right. So, we can write it like this. It is proportional to dp divided by dt. So, force is proportional to dp divided by dt. Now, we can easily show that the constant of proportionality is 1 here, and thereby it becomes F is equal to dp divided by dt, that is d by dt of mv. That's right. Thus, this equation can also be written in the following form: F is equal to, what does it become? It becomes m dv by dt plus dm divided by dt into v. That's right. So, the force can be written in this form, that is m into dv by dt plus dm by dt into v. Now, if the mass of the system is finite and it's constant with respect to time, so if m is constant with respect to time, then dm by dt becomes 0, and this gives me F is equal to m dv by dt, or this is nothing but m into a, or this is the popular form of Newton's second law of motion. The popular form of Newton's second law of motion. That's right. So second law is a law which gives us the quantitative value of force. So this can be represented F is equal to dP divided by dt, and thus we can also write it like this: F is equal to average value delta P divided by delta T, that is nothing but P2 minus P1 divided by T. This is the average force acting on an object. That's right. So remember, this external force acting on an object may accelerate either by changing the magnitude of velocity or the direction of velocity, or both. So this force may bring in change in speed or change in direction, or both. Remember, so the force is capable of doing any of these. If the force is parallel or anti-parallel to motion, it changes only the speed, no change in direction. Right? If the force is acting perpendicular to the motion, then it changes just the direction, but there is no change in speed. You have come across with such examples. So I'm just writing it once again. If the force is parallel to motion or anti-parallel to motion, of course, then there is a change in speed and no change in direction. And if force is perpendicular to motion, then there is a change in direction and no change in speed. And if force is at an angle with respect to motion, then both speed and direction undergo a change. Important concept to be kept in mind. So this is about second law of motion. Third law. A very popular law. According to this, for every action there is an equal and opposite reaction. It means if there are two forces or there are two objects, for example an object A and object B, for example you can consider them to be charges Q and QB, they exert and they experience same amount of force. Force on A by B, force on B by A are equal to each other. So force on A by B is equal to negative of force on B by A. A very well known law. These are generally known as action-reaction pairs, but you don't know which is action, which is reaction. There is nothing like one is action and the other is consequence. Both of them exist simultaneously. And also remember that the action and reaction always act on different bodies. That's right? Good. So the three laws give us the idea about the role of force on an object. First one tells us force is required to change the state of motion. Second one tells us if you apply a force, what is the change in the acceleration or what's the acceleration, etc. Third one tells us that what happens if I consider or compare the forces on two interacting objects. Now to understand these things, we also need one more very important idea, that is the idea of impulse. In the case of impulse, what happens is that a very large force acts on an object for a short duration of time. It starts acting on an object for a short duration of time. And this is given by, the impulse is given by the product of force into the short interval of time. So I is equal to F into delta t. Or we can also consider if it is a very short interval of time, then we can write di is equal to f dt, and the total change in the impulse is given by integral f dt. And this impulse is measured in terms of change in momentum. This impulse, you know that f dt is nothing but change in momentum, so it is delta p, which is nothing but mv minus mu. That is nothing but f delta t, of course. So impulse is nothing but f delta t, which is change in momentum, final momentum minus initial momentum. Now if you consider a force versus time graph, for example, assuming the force to be constant, then the area below this curve gives you the impulse. The area gives you the impulse acting or impulse provided by that large force, right? There are various examples for this concept in daily life. For example, a seasoned cricket player, while catching a ball, lowers his hand and he pulls it towards himself, such that the act of catching the ball lasts for a longer duration of time, such that he increases the time and thereby the force exerted by him while catching is decreased to compensate for that impulse. That's right. Or if you consider say one more example, the train bogies are provided with buffers. The role is something like this: they increase the time interval of jerks during changing, and hence they reduce the force with which the bogies or compartments pull each other, right? So this is a very important concept which is quite useful in handling numerical problems. Some important points regarding Newton's laws of motion, some important applications. Suppose I consider the first one. You know, we have already seen F is equal to dP divided by dt. Now, if force is 0, then you know dP by dt is also 0, which implies that dP is 0 or the change in momentum is 0. Correct? Change in momentum is 0 implies momentum is equal to constant. This is what is known as law of conservation of momentum. Law of conservation of momentum. Linear momentum. According to which, if the net force acting on an object is 0, then its linear momentum is conserved. You know, if linear momentum is conserved, there is no change in momentum, right? It generally implies that for a constant mass system, its velocity is also constant. So velocity does not change if the mass of the system is constant. This is law of conservation of momentum. Second, suppose I consider two objects. So this is a direct application which is quite useful in handling numerical problems. Let's assume that there are two objects of masses m1 and m2, all right, and suppose same amount of force acts on them, okay. Initially they are at rest, and now our objective is something like this. We want to find out the ratio of time t1 to t2 such that they have same displacement. First of all, same displacement. So two objects, same amount of force acts on them, and our objective is to find the ratio of time such that same displacements occur. If that be the case, T1 by T2 is equal to square root of m1 by m2. Suppose they have same final velocity, then the ratio of time T1 by T2 is equal to m1 divided by m2. I want you to remember these results, okay, quite useful results, and they have same momentum. Then T1 divided by T2 is equal to 1 by 1, 1:1. That means they take the same amount of time to have the final momentum. That's right. Thus, if you consider two objects, then of course of different masses under the influence of same force, then the ratio of the time required for them to have same displacement is root of m1 by m2, same final velocity m1 by m2, same final momentum 1. One more application. Suppose we consider two objects of masses m1 and m2 connected by a spring. Let's assume that they are pulled apart with same forces F each. Then m1a1 is equal to m2a2, and their accelerations a1 by a2 are in the ratio m2 divided by m1. So remember these simple results, quite useful. Newton's laws of motion can be applied to arrive at various results. In most of the problems, we consider Newton's laws of motion along with something known as free body diagram. What is that free body diagram? Free body diagram is a diagram which shows forces acting on different parts of the same system by considering them differently. How do we show? We use an arrow. Arrow head sits on the object and arrow tail sits on the object, and arrow head indicates the direction of the force. It is along the direction of the force. For example, let us consider a very simple case. Here is an object kept on the ground. Then what are all the various forces acting on this? First of all, weight mg, and then normal reaction. So I show the forces like this, mg and n, normal reaction or normal force. So while drawing the free body diagram, what are all the forces that you need to take? Number one, weight. I suggest you to follow this sequence, it becomes easy. Then we have normal reaction or normal force. Then tension in the string, if there is any string. Spring force, if there is any spring, of course. And any other force. There may be any other force. For example, there may be electrostatic force, there may be magnetic force, or there may be a buoyant force or upthrust, etc. So these are all different forces. And finally, friction. Friction, later we will revise that, is a self-adjusting force. So my suggestion is to keep the force of friction at the end. So while drawing the free body diagram, follow this sequence: weight, normal reaction, tension, spring force, and any other force, and finally friction. For example, if I consider one more example here, an object which is suspended, then what are all the forces? Yes, you guessed it right, mg down and tension T up, correct? Or if I consider, say, I have applied, or say I have sprayed some charge and there is an electrostatic force in the downward direction, then what is the additional force? Yes, on this charge there is an additional force EQ, and of course along with mg and probably the tension in the string is different this time, T dash. So depending on the situation, you need to draw the free body diagram appropriately, right? Now what if the system is accelerating? If the system is accelerating, then the net force will not become 0, and in such cases you have to consider Newton's second law of motion. Let us now take up one such important application in the form of apparent weight of an object in a lift. Apparent weight of an object in a lift. Let us consider a couple of cases. So here is the arrangement. The lift, and let's assume that this is attached to something and is capable of moving, accelerating up or down. This is the object whose mass is m. Now couple of cases. Number one, if the object is at rest, the acceleration of the lift is 0. So now the lift is at rest, or it moves at constant velocity, rest or constant velocity. It implies that the acceleration is 0. Then you know that mg and n are equal to each other, and the normal reaction is a measure of its apparent weight. Thus we can say the apparent weight of the object is equal to its actual weight mg. So the true weight or the apparent weight is equal to true weight. Case number 2. Let's now assume that the lift is accelerating up with an acceleration a. So this is the lift which is accelerating up with an acceleration a. Mg is the force down and normal reaction is the force up. So now what is your equation for motion? Ma is equal to n minus mg, or n is equal to m into a plus g. But you know normal reaction is a measure of apparent weight. So I can write apparent weight is equal to m into a plus g, or this can be written like this: mg into, what is it going to be? It is going to be 1 plus a divided by g. But you know this is its true weight, so I can write true weight or actual weight into 1 plus a divided by g is its apparent weight. Do you notice that the apparent weight in this case is greater than the true weight or actual weight? Yes. So if the lift is accelerating up, then the true weight and apparent weight are not equal to each other. Apparent weight is more than true weight. Case number 3. This time the lift is accelerating down. The lift accelerates down, forces are mg, n, and your equation of motion becomes ma is equal to mg minus n, or n is equal to m into mg minus ma. Is that correct? Yes, mg minus ma. Or it further simplifies to mg into 1 minus a by g, or true weight into 1 minus a by g, or apparent weight is equal to true weight into 1 minus a by g. Is that correct? Yes. Which implies that the apparent weight is less than the true weight. Apparent weight is less than the true weight. Now the question is, what if A is more than G? If A is greater than G, then the apparent weight will be negative. It implies that the object actually sticks to the roof. It is pressed against the roof. Pressed against the roof, and it is not on the floor. It is not present on the floor. That's right? Okay. Suppose I consider this case in which the object is in free fall. Sorry, not the object, the lift is in free fall. That means the acceleration of the lift is equal to G. So it is falling freely, and this time what are all the forces? mg, n, and your equation for motion is ma is equal to mg minus n, or n is equal to mg minus ma. mg minus ma, A is g, this is 0. So the normal reaction is 0, or the apparent weight is equal to 0. Apparent weight is equal to 0. Simple case, right? Good. Let us take up one more case. So this time, this is one of the common types of problems which is asked frequently in competitive examination. A monkey or a person climbing up a rope. Climbing up a rope. So here is a rope, and monkey is climbing up the rope. Now first case, now if the monkey is climbing up at constant speed, its velocity is constant this time because it is a one-dimensional motion, then what are all the forces? The forces are mg and of course t, that is t this time, t. So it is moving at constant speed, or velocity is constant, implies that the acceleration is 0. That gives us t is equal to mg. Simple case. The tension in the rope is simply equal to the weight of the monkey. Second case. This time it moves up at an acceleration. At an acceleration a. So now what is the equation? This time mg, t and ma. So equation becomes ma is equal to t minus mg, or t is equal to, what is it going to be? It is nothing but m into a plus g, or g plus a. So the tension in the string becomes more. If the monkey starts climbing up the string, the tension in the string becomes more and more. If it climbs up with greater acceleration, the tension also becomes greater. And if the tension exceeds what the string can withstand, that is its breaking point, the string will snap. Suppose I consider this case, it now moves down with an acceleration a. So this time what are all the forces? mg, t, and it is climbing down with an acceleration a. So what is the equation? ma is equal to mg minus t. Is that correct? Yes. Or what do we have? T is equal to m into g minus a. That is correct. So the tension becomes mg minus ma. Now again, one more time, what if A is equal to G? Then the tension in the string becomes 0. The tension in the string becomes 0 in this case. Is that correct? Yes. Let us take up one more case. These are all typical types of problem varieties as far as competitive examination is concerned. Let us consider a moving carriage or say moving vehicle and a mass is suspended from this moving carriage. Okay, so this is the arrangement. Here is a moving carriage and it is moving and the mass is suspended. It is like a pendulum. Now let us consider a couple of cases here. Let us see what are all different cases and how to solve them. Now if this carriage is at rest, case number 1, it is at rest or moves at constant velocity, then the tension is equal to mg. The tension in the string is equal to mg. Second case, let us assume that this carriage is now moving up. It is moving up. Moving up at an acceleration a. So what is the tension in the string? This is nothing but m into g plus a. Did we see that earlier? Yes. How? mg t ma. So ma was equal to, what was it equal to? T minus mg. So t is equal to m into g plus a. What if I consider it to be moving down at an acceleration a, then t is equal to m into g minus a. Similar case. Suppose I consider one more case, freely falling. If it is freely falling, the tension is 0. You have seen that. Now let us consider one more case. This time the same thing is accelerating horizontally. The carriage is accelerating horizontally at an acceleration a. So this is the construction. So this time the mass experiences a pseudo force, or if we are working from the reference frame of this carriage, the carriage frame, then there is a pseudo force and the string or the pendulum is not horizontal anymore. But seen from the carriage frame, what are all the forces? How do I write it? T is present here, and how do I write this? This is theta. Then I can resolve this t into components. How do I write that? So if I resolve this, it's going to be t cos theta and t sin theta, and t cos theta is equal to mg and t sin theta provides the necessary force ma. Therefore, from this set of equations, we notice that if I square and add, I get t is equal to square root of what? G square plus a square into m. So t is equal to m root of g square plus a square. If I take the ratio, I get tan theta is equal to a by g, or theta is equal to tan inverse a by g. So while working with the problems of this kind, you need to take the concept of pseudo force if you want to work from the accelerating frame. What is that pseudo force? It is an imaginary force. What is the direction of this force? This is against the direction of acceleration. Correct? Is it so? Check it for yourself. Then, what is the magnitude? It is mass of the object into acceleration of the frame. So, value of pseudo force is mass of the object into acceleration of the frame, remember. So, by doing so, we can easily solve the problems when the reference frame itself is moving. So, these are all some simple examples as far as competitive examination is concerned, some simple cases. Before I take up different cases corresponding to motion of a block, let us take up one more case of Newton's laws of motion, that is system of variable mass, a variable mass system. We had learnt that force is given by m dv by dt plus v dm divided by dt. So, in such cases where the mass itself is changing with respect to time, for example, you can just assume there is a water tanker which leaks out water, or maybe a conveyor belt on which the mass is placed continuously, or maybe the case of a rocket propulsion where the exhaust gases are thrown out continuously. The system maybe is gaining mass or maybe is losing mass. So, if that be the case, Newton's law of motion, third or rather second law, becomes F is equal to m dv by dt plus v dm divided by dt. Now, if the mass of the system changes, this is a critical case. So, if the mass is changing and the velocity of the changing mass, that is the mass which is escaping or say added, is constant, then dv divided by dt is equal to 0. So, what happens? We have the equation F is equal to v dm divided by dt. That's right. F is equal to v dm divided by dt. Observe that the mass which is added or say lost retains its constant velocity. For example, if see, these are some of the important examples from your competitive examination perspective. Let us consider, say, a machine gun. Example of a machine gun. Let's assume that n bullets are fired per second or say per unit time, and mass of each bullet is m. Then the force required to hold the gun F is equal to v into dm divided by dt, and this is nothing but F is equal to v into m into n, or this is mnv. Okay, so remember this one. V is the velocity of each bullet, n is the number of bullets fired per unit time or say per second, and m is the mass of each bullet. Then the force required to hold the gun is given by v dm by dt, and dm by dt, that's the rate of change of mass, is nothing but mn, and that is finally mnv as far as force is concerned. One more. Let's assume that sand is dropped on a conveyor belt. Sand is dropped on a conveyor belt, and now I want to keep the speed of the belt constant. Speed of the belt should be constant. Then the force I need to apply to keep the velocity of the belt constant. See, if I don't apply any force at all, then because of more and more mass, the belt loses its velocity. But I want to keep its velocity constant, so I need to apply force. Then v into dm divided by dt is the force required to keep the velocity of the belt constant here. What is that dm by dt? That's the rate at which the sand is dropped. What is that v? V is the speed at which it is added. Or one more example. These are all typical concepts which are quite frequently asked in your competitive examination. Let's assume that there is a pipe and this is of cross-sectional area A, and a jet of liquid, maybe water, is coming out, and it is coming out at a speed v. Let's assume that this water jet is going to strike a wall. With a velocity v. Then the force applied by this water jet or water stream on the wall is given by a v square into rho. A v square into rho, where rho is the density of the liquid. Most often this happens to be water. So if a jet of liquid coming out from a pipe of uniform area of cross section A strikes a wall normally, perpendicularly, remember, then the force applied by the jet on the wall is AV square into rho. So these are some applications of variable mass system. We'll take one more here, that is the case of motion of a rocket propulsion case. Suppose I consider here, in the case of a rocket ejecting gases, and let's assume that the gases are ejected at a relative velocity v. So this is the velocity of the gas with respect to rocket. Then Newton's second law tells us that external force plus v relative into dm divided by dt is m into a, right? And this v relative into dm by dt is the reaction force exerted by the ejected gases on the rocket, and this is many a times referred to as thrust. So if the question is about thrust, then you will be calculating v relative into dm by dt. But if you are asked to analyze the motion, remember F external plus v relative into dm by dt is equal to ma. Now suppose I consider, in the absence of air resistance, and if the rocket moves with an acceleration a then the thrust becomes V relative dm by dt is equal to m a, and of course g is minus of minus, so this becomes ma plus mg. Remember, g is always down, so this becomes minus mg. So this becomes, in all, V relative into dm by dt, that's nothing but thrust, is equal to ma plus mg. Suppose the rocket moves up with constant velocity. I am writing here, what if the velocity of the rocket is constant? Then what is the thrust equal to? Then the thrust is simply V relative dm by dt, and what is that equal to? This is simply equal to mg. That's right. So the thrust is simply equal to mg. So these are some of the important cases as far as applications of Newton's law in non-inertial frame is concerned. That's right. Variable masses, of course. Now let us take up a few important shortcuts and tricks which are quite useful in handling numerical problems. Then we will take up friction and then some general cases, of course. Suppose I consider motion of a block on a horizontal smooth surface. These are some important results, okay? Better remember, motion of a block on a horizontal smooth surface. First case, F is horizontal. There is a force acting horizontally. And this is the case, force is exerted along this direction. What are all the forces? mg, n, and thus the corresponding results are n is equal to mg and its acceleration is f divided by m. Simple case. Second, so this time force is at an angle. Same setup. F is at an angle theta. Now what are all the forces? I have F cos theta, I have F sin theta, I have N, I have mg. So this time, what are all the equations? N is equal to mg minus F sin theta, and the acceleration is F cos theta divided by m. Correct? Remember, the earlier case is a pull. So now let us consider a force at an angle, but this time it is push. So I am exerting a force F along this direction. It is a pushing force, such that with horizontal the angle is theta. So what are all the forces again? This is F cos theta, this is F sin theta, this is mg, and this is n. That's right. So what are all the equations? N is equal to mg plus F sin theta, and acceleration is F cos theta divided by m. So if I consider this case, the motion of a block on a horizontal smooth surface, these are the results. Now we will consider motion of an object on a smooth inclined plane. First case, a fixed inclined plane. Now, what are all the forces? N mg, and this is accelerating down, and of course this angle is theta. So what are all the forces and what are all the equations? You can resolve that mg into components. We'll notice that this turns out to be mg cos theta, this turns out to be mg sin theta. Is that correct? Yes. So n is equal to mg cos theta, and acceleration down the plane is simply g sin theta. Now let me consider one more case. This time let's assume that the inclined plane is moving horizontally. At an acceleration a, or say I'll take this b to make the things easy. So observe that this is accelerating at an acceleration b, and again the same block, same setup, theta, n, right? Your mg is vertically down, and this is accelerating down at an acceleration a. Remember, this is accelerating at b towards right. Now the results are here. I am writing the results straight away. N is equal to m into g cos theta plus b sin theta, and the acceleration a is equal to g sin theta minus b cos theta. So if the inclined plane is also accelerating, then the result is here. Let us consider one more case. Connected bodies. We have two bodies in contact, okay, like this. This is of mass m1, this is of mass m2, and we apply a force F from left. Two bodies are kept in contact, force is applied on the block of mass m. Now what are we calculating? We are calculating two things. One, acceleration of the system. Acceleration of the system is F divided by m1 plus m2. And we want to find out the normal reaction between these two also. That means normal forces exerted on each other. That is the force of contact. Contact force, or say normal reaction exerted on each other. I'll call this as N dash. Then N dash is equal to m1 into F divided by m1 plus m2. I have not shown the calculations here. It is simple. You draw the free body diagram and analyze. Suppose I consider this case, m1 and m2. This time I am applying the force from this side. Say F is applied from this side. Guess what? Acceleration is again F divided by m1 plus m2. The normal reaction between these two, suppose n double prime is the representation, n double prime is equal to, guess what should be the equation? You are right, m2 F divided by m1 plus m2. Isn't it? Simple. Suppose you consider the case of three blocks, block 1, block 2, and say block 3. Their masses are m1, m2 and m3. I am applying a force F here, and the force between these two is say N1, the force between these two is N2. Then the results are here. acceleration is F divided by m1 plus m2 plus m3 as expected. Then n1 is equal to m2 plus m3 into applied force F divided by m1 plus m2 plus m3, and n2 is equal to m3 into F divided by m1 plus m2 plus m3. You may also notice what if the force is applied from the other side. I will leave it to you. Let us consider connected bodies again, this time with strings, not in contact but with strings. For example, I am considering this case of two blocks connected by a string. Forces are masses are m1 and m2, and I am applying a force F, and the entire system accelerates towards right with an acceleration A, and T is the tension in the string. Acceleration is clearly F divided by m1 plus m2, and the tension in the string is m1 F divided by m1 plus m2. Correct? Simple. But this time, can I apply a pushing force? No. If I apply a pushing force, both the blocks cannot accelerate. The tension in the string becomes 0. The tension in the string becomes 0. One more case. This time I have m1, m2 and m3, and I am applying a pulling force F, and this entire system is kept on a smooth horizontal surface. What are the relations? Acceleration of the system is simply F divided by m1 plus m2 plus m3. Suppose the tension in this string is T1, the tension in this string is T2. Then T1 is equal to m1 F divided by m1 plus m2 plus m3. T2 is equal to, this is going to be m1 plus m2 into F divided by m1 plus m2 plus m3. Correct? All right. Let us consider one more case. I am considering a pulley mass system. A light and smooth arrangement, m1, m2, assuming that m2 is greater than m1, the system accelerates down along this direction, and this also accelerates up along this direction. Now, what are all the equations for motion? Acceleration is nothing but net force, which is net pulling force, which is m2 minus m1 into g divided by m1 plus m2. Is that correct? Yes. The tension in the string is equal to 2 m1 m2 g divided by m1 plus m2. So this is assuming light pulley. Suppose the mass of the pulley is also taken into consideration, then the result will be different. we'll deal with such cases when we take up rotational mechanics. One more case. This time we got a block connected to a pulley mass system through this arrangement. This is of mass m2, this is of mass m1, and assume that the motion happens along this direction, and this is of course ideal one. Then the acceleration of the system is m2g divided by m1 plus m2. Why? Because the net pulling force depends only on m2, while the motion of m1 happens horizontally and its motion is not controlled by gravity. And the tension is of course m1 m2g divided by m1 plus m2. One more case. This time I am putting it on an inclined plane. Let's assume that it is put on an inclined plane like this. Let's assume that this is theta and this block is of mass m1 and this passes over this setup, this being m2. Let's assume that it accelerates up along this direction and down along this direction respectively. Now for this setup, the acceleration A is equal to m2 minus m1 sin theta into g whole divided by m1 plus m2, and the tension T is equal to m1 m2 1 plus sin theta divided by m1 plus m2. Suppose the system is in equilibrium, then m1g sin theta is equal to m2g, or we can write m1 sin theta should be equal to m2. This is a special case. In fact, we can write it in the general form like this. Suppose this angle is alpha, this angle is beta, and we have block of mass m1 here and another block of mass m2 here. Assuming the acceleration along this direction, say, then the acceleration is equal to, this turns out to be m2 sin beta minus m1 sin alpha into g whole divided by m1 plus m2. And the tension in the string is m2 sin beta minus m1 sin alpha into g, that's correct. The tension in the string is m1 m2 divided by m1 plus m2 into sin alpha plus sin beta. So remember these results, the results what we discussed are quite important. Okay, so remember these important results, they will be quite useful for handling numerical problems. Alright. One of the important types of forces in the present context is that of friction. Let us take up this one. So what is friction? You know, friction is a force which tries to oppose the relative motion between the objects. That's right. And we know that this friction can be understood in terms of static friction, kinetic friction, and also rolling friction, whose origin is slightly different from those of static and kinetic friction. If the object is at rest and the force of friction comes into play, it is static friction. If the object is moving and the force of friction comes into picture, kinetic friction. So let's try to understand these things. Remember, friction is a self-adjusting force. Okay, remember this important idea. So now, if an object is stationary and I start pulling this then initially there may not be any motion. So force of friction comes into picture along this direction, which is static friction, and I keep on pulling harder and harder. This static friction starts growing in size or say magnitude, and there comes a stage at which the object just yields. The object just yields, and when the object just yields, this corresponds to maximum static friction, and that maximum static friction is known as limiting friction. This limiting friction, which is represented by F limiting, can be shown to be equal to mu n. Limiting friction is equal to mu n, and this mu, that is coefficient of static friction, is an indicator of the extent of roughness between the surfaces, coefficient of static friction. So we can write coefficient of static friction as limiting friction divided by normal reaction. Normal reaction. And in general, coefficient of static friction is greater than that of kinetic friction. So coefficient of static friction is more than kinetic friction, and kinetic friction is given by mu k into n. So kinetic friction, or say force of kinetic friction, or say force of friction during motion, is mu k into n. So in general, remember, kinetic friction is less than static friction, coefficient of kinetic friction is less than coefficient of static friction. Let us consider some important applications in this case. Okay, suppose I consider an object which is being pulled, a block which is being pulled. If F is the force applied, and if the object is stationary, then static friction is equal to force, as long as the object is not moving. Now the object is at the verge of motion. Object is at the verge of motion, then static friction is equal to limiting friction, and that limiting friction is equal to mu n. Suppose this time the force applied is more and the object starts accelerating, then what comes into picture is the kinetic friction, and the acceleration of that object is applied force minus kinetic friction divided by its mass. So three simple cases. Suppose I am applying force at an angle. Let us see what to do. So these are different cases, of course. I am applying a force along this direction at an angle theta. Then force of friction comes into picture along this direction. So how much is that? You can easily calculate that. Normal reaction is along this direction, and F sin theta is along this direction, and F cos theta is along this direction, isn't it? So this limiting friction is right. So now pulling force towards right becomes F cos theta, isn't it? While what we have is F sin theta plus n balancing mg, or n becomes mg minus F sin theta. So your force of friction, that is limiting force of friction, becomes mu n, that becomes mu into mg minus F sin theta. Remember, this is limiting friction. If the object is not moving, remember, this is when the object yields. However, if the object is not moving at all before the limiting friction is reached, then F is equal to F cos theta. Understand this concept. Suppose I apply a pushing force. Then what are all the results? This is theta, this angle is theta. I have f cos theta here, I have f sin theta here, and mg here, and of course n here, and force of friction is along this direction. And remember, if the object is considered before yielding, that means about to move, then force of friction is equal to f cos theta. But when the limiting case is reached, then f limiting is equal to mu n, that becomes mu n. What is that n equal to? How do we get it? Mg plus f sin theta is equal to n, or what do we have? This is mu into f sin theta plus mg. So this is the limiting friction. This is the limiting friction. That's right. Simple cases, of course, for an object which is moving on the horizontal surface. What if I consider it on an inclined plane? Earlier we considered a smooth inclined plane. This time we will consider a rough inclined plane. Then remember, some important results are here. This is theta and the block is of mass m and it slides down. Remember, it slides down. It is accelerating down. Some of the important results are here. Number 1, net force acting on the object along this direction, along the direction which is in the downward direction, is mg sin theta minus mu k into mg into cos theta. You may wish to write down these details. Net acceleration is equal to g sin theta minus mu k g cos theta. Time taken to reach the bottom, t is equal to square root of 2l divided by a. That's right. T is equal to square root of 2l divided by a, where l is this length. Final velocity, assuming it to start from rest, is square root of 2gl into sin theta minus mu cos theta. So remember these results. If an object is sliding down an inclined plane, then F net, A net, time taken and final velocity are given by this set of equation. Okay. So it is better if we can compare these results. For example, smooth inclined plane versus rough inclined plane. Acceleration, what is that acceleration? This is g sin theta on the smooth inclined plane, and this time what is the acceleration? It is g sin theta minus mu g sin theta. It is mu k in fact, but most of the times, you know, static coefficient and kinetic coefficient are taken to be same. Not necessarily all the time, even then. Time of descent, that is what we saw. Time of descent is given by square root of 2l divided by g sin theta. However, in this case it is square root of 2l divided by g sin theta minus mu g cos theta. Final velocity, v is equal to square root of 2gl sine theta, while in this case it is square root of 2gl into sine theta minus mu cos theta. That's right. So if you observe carefully, if I call this as subscripts as S to indicate smooth, and these are R to indicate rough, what do we notice? Do we notice that AS is less than AR? Correct? Isn't it? Or the other way around? The other way around. AR is less than AS. Correct? AR, I am writing it here again. AR is less than AS. TR is more than TS. And VR is less than Vs. Remember these results. What if I consider motion of an object, or say motion of connected bodies on rough surface? Let us take up this last part. Motion of connected bodies on rough surface. First, I will consider this case. There is a block and there is an inclined, there is a pulley mass system, and this is the arrangement. This is M2, this is M1. Now, you may notice that force of friction acts along this direction, and of course the tension is T in the string, correct? And assuming the system to accelerate in the downward direction, then the acceleration of the system is equal to m2g minus mu m1g divided by m1 plus m2. How to get this one? Simple. We need to draw the free body diagram. On m2, the forces are m2g down, T up, and of course the system is accelerating down. On m1, the forces are m1g, normal reaction N, tension is pulling it along this direction, and force of friction is in this direction, and this system is also accelerating towards right. So upon solving the equations, we get A is equal to m2g minus mu m1g divided by m1 plus m2, and the tension is equal to m1 m2g divided by m1 plus m2 into 1 plus mu. 1 plus mu. One more case. We have an inclined plane C. Theta, and of course there is a pulley mass system M1, and this is M2. Now assume that the system is accelerating down. Then what are all the forces? On M2, we have M2g, T, and accelerates down. M1, what are all the forces? M1g vertically down, normal reaction along this direction, T in this direction, and force of friction in this direction. With that, we have the results here. Acceleration once again is an unbalanced force. What is the unbalanced force here? It is m2g minus m1g sine theta minus mu m1g cos theta. Unlike the previous case, we have this additional term, whole divided by m1 plus m2, which is the net force in the downward direction, or say net mass which is moving. The tension in the string is m1 m2g divided by m1 plus m2 into 1 plus sin theta plus mu cos theta. That is right. So, for an inclined plane of this kind, the result is here. One more example. We have this setup. See, this is say theta 1, this is theta 2, and we have a block of mass m1 and another block of mass m2. Assume that it accelerates in this direction. Then you can write the forces, right? Both the blocks experience friction in this case. And if we consider the forces, you will have m1g tension, n1 force of friction, m2g n2 tension and force of friction. This is F1 and this is F2. So, upon simplification, you get the following result. Acceleration is equal to m2g into sin theta 2 minus mu cos theta 2 minus m1g into sin theta 1 plus mu cos theta 1 whole divided by m1 plus m2. And the tension in the string can be obtained using the following equations. So, what is that? What are the two equations? T minus m1g into sin theta 1 plus mu cos theta 1 is equal to m1a, and m2g into sin theta 2 minus mu cos theta 2 minus t is equal to m2a. So, the last part is kept as your exercise. Alright. So, learn how to play with these system of connected objects, string mass system, etc. So, with this problem or with this concept, we come to the end of this discussion, the discussion of this particular chapter, which is one of the very important chapters also. The key ideas are very simple. Remember, the key ideas are something like this. The key ideas are based on Newton's laws of motion with applications. What are all the applications that we have used? Basically, free body diagram. So, I am writing it here. It is basically free body diagram and Newton's second law of motion. So, most of your problems are based on free body diagram and Newton's second law of motion. Thank you very much.